In this next video, we're going to learn about a property called heat. And we're going to see that as this property is added to a certain object, that object is going to increase in its temperature, right? Heat is a form of thermal energy, and when this thermal energy is absorbed by something, that it's going to increase in its temperature. However, we're going to see the distinction that temperature is not the same as heat, and how we track those two different properties is very essential, because while we may have a certain amount of heat that's given off, right? If you can feel a certain amount of heat coming from a small flame or a fire or something like that, the object that we place in front of that heat source will gain different amounts of temperature based on its own properties. And we're going to see how this property of a substance called a specific heat can be calculated and tracked and better understand the relationship between heat and temperature. We're also going to see how when we look at these temperature calculations, this heat and temperature type of relationship, that the driving factor is that energy, like mass, is going to be conserved. And so if something is to lose a certain amount of heat to something else, that it's going to be equal, right? If an object loses a certain amount of heat to another object, that object is going to have gained that amount of heat. And if that object didn't happen to gain all of that heat, then there must be something else that's gaining the rest of the heat, right? That we don't have a gaining or losing of energy overall while these processes are occurring. And we're going to see how we can use this conservation of energy to learn more about chemical reactions through calorimetry by isolating the heat flow of a reaction, calculating the temperature that the isolated system is able to gain or lose, and then draw conclusions about the heat that occurred from the reaction that we've isolated within that calorimeter. So with that, why don't we go ahead and jump into the video. So we've discussed a little bit about how chemical reactions have changes that are associated with them, and how when we have a reaction, we can either give off or absorb energy in the form of heat. But what about non-chemical reactions, right? What about just something warming up or cooling? How do we track energy associated with this temperature change? And so I would first ask, is temperature the same as heat? And the answer is no, it's not exactly the same, because temperature is the average kinetic energy of a substance, while heat is an amount of energy. And so therefore, when we have more temperature, a higher temperature, while it is associated with a greater amount of thermal energy, it's not exactly the same thing, right? And this is partially because different substances have different changes in temperature when heat is applied. And this characteristic is called the heat capacity, and we state it as Q over delta T. And essentially all this means is that this is the heat required to increase the temperature of something 1 degree Celsius. If we have an object that it takes a lot of heat to increase 1 degree Celsius, that has a large value of capital C. And if it doesn't take very much heat to raise that 1 degree Celsius at all, then we have a lower capital C. As such, C has the units of energy per degree Celsius, therefore joule per degree Celsius, or Kelvin, right? We know that the increment of degree Celsius, or Kelvin, is the same. And so let's take a look here at an example, right? An object takes C joules, a certain number of joules of heat to increase its temperature 1 degree Celsius. And if we were to consider two identical, not identical, but the same material of pan, but one is much larger than the other, well, the large pan is going to have a greater heat capacity, right? It's going to take more heat to raise this large object 1 degree Celsius versus the small object. And so let's say that if 18,100 joules of heat are applied to the small pan, it goes up by 50 degrees Celsius. Well, we would say that the C for this pan, right, the heat capacity is this amount divided by 50 degrees Celsius, so 18,140 it should say in the top part. And therefore we get a heat capacity for the small pan of 336 joules per degree Celsius. In other words, it takes 363 joules of heat to increase the temperature 1 degree Celsius. And now let's take a look at the large pan, and we say, well, if we put in that same amount of heat, it increases by 10 degrees Celsius. And therefore, the heat capacity is going to be 1,814 joules per degree Celsius. Just take the amount of heat, divide by the change in temperature, and now we have this larger heat capacity for the larger pan. Right? Larger objects have larger heat capacities. But the challenge is that we don't really want to find a new heat capacity for every single object. So if both pans are made of iron, let's take their masses, right? And let's say we find the small pan has a mass of 808 grams with a heat capacity that we just calculated, and that the large pan has a mass of 4,040 grams with the heat capacity that we just calculated. Well, what we notice here is that given they're the same metal, right, they're both made of iron, the same substance, the large pan has 5 times the heat capacity, but it also has 5 times the mass, right? It takes 5 times as much energy to increase it 1 degree Celsius, but that's because there's 5 times as much of it. And so what's far more useful is to define what's called the specific heat capacity, which is an identity of a substance. And we define this as the heat it takes to increase 1 gram of the material by 1 degree Celsius or 1 Kelvin, right? And we call this the specific heat capacity, which again is not based on the object, but it's based on a gram of that object. And so we can rearrange this to say the very useful Q equals mc delta T, which basically relates the amount of heat that's added to an object of a certain material, of a certain mass. C, lowercase c here, the specific heat capacity, is an identity of the substance, and m is, of course, its mass. When we calculate this specific heat capacity for both pans, of course, we find the same result, that we get the specific heat capacity of iron, which is 0.449 joules per gram degree Celsius, right? So again, heat capacity, big C, that depends on the object. And in general, especially in this course, we're not going to use that very much, but still it does come up sometimes, right? Like if you're taking a lab where you do calorimetry, you may have a enclosing device that has some amount of heat it absorbs, but is made of different parts. So you may define a big C heat capacity based on that. But by and large, we're going to be using this specific heat capacity as we are going to want to define the heat capacity not based on a specific object, but on a material. And so we've shown here, based on this calculation, that iron has a specific heat capacity of 0.449 joules per gram degree Celsius, and that's regardless of which pan the iron is in. So here we have a table of specific heat capacities from our OpenStax text, and we'll notice that the trend is a bit different from what we may have expected, right? Water has a really large specific heat capacity, right? 4.184 joules per gram degree Celsius. Where, perhaps some things that we would think of as like heavy or hard to change the temperature of, like the metals, like iron, actually have a heat capacity, a specific heat capacity that is like a tenth of water's specific heat capacity. So kind of a curious result, right? And definitely something to keep in mind. Note as well that water vapor and ice have different specific heat capacities than water, so the phase here does matter quite a bit as well. Okay, let's jump into some practice here. Let's say if a 50 gram sample of aluminum increases by 15 degrees Celsius, well, how much heat did it absorb, right? If it increased temperature, it must have absorbed heat. So how much heat was that? Think of the equation we just set up for the specific heat capacity, right? Q equals mc delta T. Go ahead and pause the video and let's see what you come up with. All right, hopefully you were able to come up with a solution. This is the correct one, the 672-ish joules. And we get this again from Q equals mc delta T. And we start with the specific heat capacity for aluminum, which we want to get from this table. So it's 0.897 joules per gram degree Celsius. We can see that for solid aluminum. The mass is 50 grams. The change in temperature is an increase of 15 degrees Celsius, so positive, which will make Q be positive as well, which is a good thing because we're absorbing heat. And so therefore we calculate based on Q equals mc delta T, and we obtain our final value. So the question states that a 32.5 gram cube of a metal that has an initial temperature is submerged into water that's at a 15.4 degrees Celsius temperature, and that at equilibrium we reach a temperature in the middle, which shouldn't be too surprising, right? If we have a hot object and a cold object, we should meet in the middle. So what we want to know is what is the specific heat of the metal, because if we identify that, then perhaps we can identify the metal. And keep in mind that the specific heat of the water is 4.184 joules per gram degree Celsius. And so the first question I would pose in directing your way here is, when we get to thermal equilibrium, which of these components is going to be at 17.3 degrees Celsius? And hopefully this is one that you've made your way towards as well, but if not, maybe pause, think about it for just a second. All right, so thermal equilibrium, we get to 17.3 degrees Celsius. And the answer here is this is the temperature for both, right? The cube started at 45.8 degrees Celsius, and in the end, they're all 17.3 degrees Celsius. So it dropped about 30-ish degrees, while the water increased about, 2 degrees, right? So this, importantly, is the final temperature for both the water and the cube. And so from here, right, let's remind ourselves on what equation relates thermal energy to temperature change, and that would be Q equals mc delta T. So based on this, right, which of the two substances are we able to use Q equals mc delta T with first? Go ahead and pause again and think about that, if you will. All right, hopefully you're able to take a look, right? Here, what's going to be equivalent, right, is the amount of heat that comes out of the metal and the heat that goes into the water. But we only have enough information to solve for the heat of one of these components to begin with, right? And hopefully we were able to determine that it's the metal, that it's the water, right? So what is the energy change of the water, right? And what we have here is we have Q equals mc delta T, right? And we can say, well, let's lay out our variables. So the Q of the water, we don't know. The mass of the water is given. This heat capacity is given as well. And because we know the final temperature and we know the initial temperature, we know the increase in temperature of the water, right? And that will be 1.9 degrees Celsius. And from this, we can calculate the heat that's associated with it, right? We know the mass of the water, we know that it is water, and we know that it increased in a specific amount of temperature, right? It increased 1.9 degrees Celsius. And therefore, we know that it was 837 joules that flowed into the water. So this is the thermal energy from the metal into the water, right? Because we're going to assume that there is no leaking of heat in our calorimeter example. And so the question now is, what is Q metal? And the answer is negative 837 joules, right? If the water gained 837 joules, the metal must have lost 837 joules of heat. And in using this value, we're going to be able to learn more about the metal. So the final question is, what is the energy change of the metal, right? And using that, how can we get the unknowns that are of our interest here? And so, we can again set up Q equals mc delta T, right? Before we didn't have the Q of the metal, we do have the mass of the metal. We want to find out the C of the metal, and the change in temperature of the metal we're also able to identify from this problem. And so now that we've calculated the Q of the metal based on the change in the water's temperature and therefore the heat that went into the water, we now know Q metal, right? Because the Q water was positive 837, and based on conservation of energy, we know that the Q metal is negative 837 joules. That energy flowed from the metal into the water, right? And so now, well, that we have the change in temperature, we have the Q, we have M, and we have C, we can do Q equals mc delta T. We can solve for the heat capacity, the specific heat capacity of the metal, and we find out that it is 0.9 joules per gram degree Celsius. And based on this table, we can see that this is awfully close to aluminum. And so it would be reasonable to conclude, maybe with some other visual evidence from the cube, if we were to have this in a more real-life experiment, that this could conceivably be aluminum, right? And perhaps not carbon dioxide. We may be able to tell those apart just by looking at them. And anyway, so this is a good example of a coffee cup calorimeter where we're able to contain the energy within a rudimentary device, right, an insulating device. And in this way, we're able to relate the heat that is gained by the water to the heat that is lost by the metal and potentially learn more about the metal.